So here is one example how thinking in terms of block vectors and rotations of the block sphere can help you to visualize certain things in quantum information science. So for example, suppose we want to construct any unitary operation on a single qubit. What is really required? What is a minimal set of resources for this? So I will claim, and let me just draw this diagram and I will talk a little bit about it. So let me take our golden diagram, which is Hadamard, phase, Hadamard. You've seen it before, right? And you'll see it many, many times. And let me add two extra operations. So let me put the phase gate alpha in front of the whole circuit, and let me just put another one, beta, at the end. Now, as you can see, this diagram is characterized essentially by three parameters. So we have alpha, we have phi, we have beta. And I claim that any unitary operation up to any 2x2 unitary operation up to a global phase factor can be essentially implemented by varying alpha, phi, and beta. And can we see it? So can you, just by looking at this diagram, say, well, yes, it kind of makes sense? Well, when you think in terms of rotations, when you visualize this operation in terms of a rotation of the block sphere, then you will say, okay, well, what do we have here? If we look at this part here, you think about our golden circuit in the following sense. Well, essentially, I have rotation about the z-axis by phi, I sandwich it between the two Hadamards. And I know that the Hadamard interchanges z and x-axis. So essentially what I have here is the rotation by phi about x-axis. The z is transformed into x due to the Hadamard operation. So the central part here, what it really does, it implements the operation, which is a rotation by phi about the x-axis. Well, of course, alpha and beta are rotations by alpha about z, and then here we have beta about z again. So now you have to just think in terms of composition of rotations, and we know that any rotation can be implemented by three basic rotations. So you just essentially rotate your three-dimensional objects by alpha about z-axis, then it follows by some other rotation about the x-axis, and you go back to the z-axis and perform another rotation about z. So that gives you some kind of a good plausibility argument that it works, right? So any rotation can be implemented as a sequence of those three rotations, and that should give you some kind of a confidence that this kind of makes sense. Of course, you know, you just can go on and do the calculations and prove that this is the case, or just write it explicitly and see that those parameters make sense. All it means, by the way, if you look at this diagram, that in order to implement any unitary operation, all we have to be able to do is to implement the Hadamard gate and implement the phase shift. So we need two types of operation in order to construct any unitary operation on a qubit of our choice. That is fine for physicists. The computer scientists are a little bit unhappy by this statement, because they say, well, that might be true, but if you look at when I say that I have just a phase gate, in fact, I assume that in order to implement any unitary operation, I have infinite set of phase gates, so because I have to be able to vary alpha, phi, and beta. Ideally, we would like to be able to implement any unitary operation with any precision using a finite set of gates. And the question is it then possible? Can we just pick up one particular phase gate and do all the constructions? Well, it is indeed, and it is certainly possible to do that. And for that, we simply pick up T gate. Let me just remind you. So we will keep the Hadamard gate, and we will pick up the T gate, and the T gate was a special phase gate that was defined by this matrix 1 on the diagonal e to I pi over 4. As it happens, the two are sufficient to allow us to implement any unitary, and if you think in terms of rotations, it allows us to construct any rotation whatsoever. It's interesting also to look at the set of gates, which will not allow you to do this. If you only consider the Clifford gates, if you look at the Hadamard, and if you look at all the Paulis, X, Y, Z, and the S gate, so if you take this set, then if you look how it acts on the Bloch sphere, so you take your Bloch sphere, and you have your z-axis here, x-axis here, y-axis here. So it turns out that if you start with state 0 or state 1, so those are the north pole corresponds to state 0, and the south pole here corresponds to state 1. And if you use any sequence of the Clifford gates, then you will be hopping on the Bloch sphere from one of those 6 points which mark the intersection of those axes with the Bloch sphere. So I have the 6 points. They actually form an octahedron, but not that it matters that much. I hope you can see what I have in mind here. So if you operate with a set of Clifford gates and you start in state 0, so you will be hopping between any of those 6 states here, which is of course not good, because you would like to explore the whole richness of the surface of your Bloch sphere. And sort of it's interesting that if you add T gate to this set, that will allow you to hop on the Bloch sphere. So in fact you can only use the Hadamard step and the T gate step, and that would allow you, by combination of different steps, explore the whole Bloch sphere rather densely. So you can actually approach any point on the Bloch sphere if you are able to implement the Hadamard and the T gate. Now the question, of course, the computer scientists, the next question, and the good question computer scientists will ask you, sort of how efficient it is. So suppose you start here, and I want you to come here to this point on the Bloch sphere. So can you, via a sequence of elementary steps defined by the Hadamard and the T gate, can you walk in this way somehow to this particular state here? Well, of course, with those sort of discrete steps, you may not be able to hit exactly, and you'll almost never hit exactly the desired final state, but you may be able to come very close with some, say, precision, or to the neighborhood of epsilon to this state. And so the good question to ask is, how many steps are needed to go from this particular state to this, if you request a certain precision. So you request that you are getting there very, very close with precision epsilon. So the beautiful theorem due to Solovey and Kitaev tells us that it doesn't actually require too many steps, and the scaling is nice, because it goes as at most polynomial functions of log 1 over epsilon with log raised to some power here. So you see, if you make this epsilon smaller and smaller, you know, then 1 over epsilon is larger and larger, but it's only logarithmic in increase here, and the number of steps that are required are of this order. So that means that we may not know exactly how to get there, but we know at least that it's possible to get there with a number of steps that scales very nicely.